Hi, I'm Mike Seaman with Eta Power. In this video, I'll introduce our new Magnetics Designer, which allows you to design and analyze custom magnetics in the context of your power converter. We'll create and analyze a custom transformer for a 36-watt offline flyback converter. Start by creating a new flyback converter by choosing New Converter Wizard from the File menu and type in your converter specifications. To simplify the analysis, we'll consider a DC to DC flyback and neglect the input filter and rectifier stages. We'll consider an input voltage from 90 to 350 volts DC, an output voltage of 12 volts, and an output current up to 3 amps. We'll click Require Isolation to look at isolated topologies. Eta Designer provides us with a list of suitable topologies. We'll choose the flyback converter. The next step is to choose a switching frequency. 100 kHz is good for our design. Clicking Next and Finish will create the closed-loop flyback converter design. This converter uses an ideal transformer model in the simulation. We want to convert this transformer to a custom transformer model. Select the transformer and choose Realize as Custom Transformer from the Library menu. The transformer symbol changes, so we'll adjust the schematic to reconnect the transformer. We will provide plenty of space for an auxiliary winding we'll add later. Now that a transformer is wired correctly, we can see the background simulation run successfully by the green check mark on the lower left-hand side of the window. Next, edit the custom magnetic by double-clicking it on the schematic. The Magnetics Designer allows us to choose the geometry and material for the core. We'll start by choosing the RM8 core from FerroxCube, and then the 3C92 material, also from FerroxCube. We'll then choose a suitable bobbin from the list. Let's look at the components of the Magnetics Designer. Here, you can specify the air gap, magnetizing inductance, and primary turns count of the transformer. Because these values are interrelated, you can specify any two of them, and Eta Designer will calculate the third for you. In addition, you can specify a leakage inductance or allow Eta Designer to calculate the leakage inductance based on the physical layout of the transformer. Finally, a table provides a list of windings in the design, including the single primary winding and any number of secondary or auxiliary windings. Edit each winding by double-clicking it on the list. Let's explore the right-hand side of the Magnetics Designer window. The Basics tab shows us a mechanical drawing of the core geometry as well as the schematic symbol of our design based on our winding choices. The Winding Layout tab shows a cross-section view of the transformer core with the winding layout placed inside the bobbin window. The winding groups can be manipulated by dragging them around the window or by double-clicking them on the list below. Finally, the Losses tab shows the estimated transformer losses in the saturation properties of the magnetic design. Core and winding losses are calculated using the simulated current waveforms from the power converter itself. In addition, Eta Designer also calculates the AC losses for each winding, including skin depth, proximity, and fringe field effect losses. Finally, Eta Designer also estimates the free air temperature rise of the device to ensure the device does not get too hot. Now, we'll start our design of this transformer. We'll exit the Magnetics Designer and run a few simulations to understand how we need to modify the design. We'll start by selecting the worst-case simulation condition by editing the design variables of the converter. We'll set the output current to the maximum value of 3 amps to look at the worst-case load. We'll also set the input voltage to the minimum value. Now, we'll run a startup transient and see that it doesn't yet reach steady state. We'll extend the startup time to 1 millisecond to view the whole transient. Now, we'll clear some of these waveforms and click the Probe button to examine the primary side current. Our primary side current is limited at 2.3 amps during startup due to our current mode control, and settles around 1.6 amps in steady state. Now we'll edit the transformer. We'll start by defining the turns ratio between the primary side and secondary side windings. Double-click on the secondary side winding in the list. We want a turns ratio of 10 to 1, so we'll start by choosing turns ratio from the pop-down menu, and then enter a value of 0.1, representing our desired turns ratio referred to the secondary winding. We get a notification indicating our transformer may be in saturation. The loss tab indicates a saturation current of 2.02 amps. Let's increase the turns count to 50 turns, which yields a satisfactory saturation current of 4.64 amps. Our core loss is a manageable 71 milliwatts. We now see that our AC loss is excessive. Let's look at the winding layout and find out why. Our primary and secondary windings are located side by side on the bobbin, preventing good coupling between the windings. The magnetic field builds up across these layers of windings and creates excessive proximity loss. We can drag the primary winding next to the secondary winding to stack the windings on the bobbin instead. This move helps reduce our total loss significantly and also reduces our leakage inductance. The next step is to add further insulation to the design. High voltage offline supplies like this one often require reinforced isolation between primary and secondary sides. We can use the Add Tape button to add effective spacing between the primary and secondary windings, or add triple Teflon insulation to one of the windings. In this case, we'll use triple insulated wire to keep things simple. Double-click on the secondary side winding and set the insulation type to triple PFA. Since the wire size is set to auto, the effective copper area will be automatically reduced such that the windings fit in the window. We can see that our AC losses have reduced substantially. The color coding of the wire indicates that the AC losses dominate the DC losses of the windings. The windings closest to the gap have the most loss due to the fringing field effects from the core gap. To reduce the loss further at the expense of the transformer cost, we can convert one or both windings to Litz wire. Here, we'll convert the secondary to Litz wire. Double-click on the secondary winding again, then choose Litz from the wire type pop-down menu. Now we can fix the total wire size to 1.1 millimeters and specify the strand gauge of the wire as 42 AWG. Eta Designer can then calculate the number of strands for us automatically. We now see that the AC losses on the secondary have been reduced substantially. Finally, we'll add an auxiliary winding to power the primary side controller. I'll add another winding and designate it an auxiliary. I'll set a turns count of 5 turns and click Flip Dot to reverse the winding's polarity on the schematic. I'll choose a small 26 gauge wire for the auxiliary winding. Okay, now I'll drag the winding on the core layout to place it on the side of the design for now. I'll resize the secondary winding to 0.9 millimeters to make it all fit. I'll click OK and revise the schematic to reconnect the original windings and to connect a dummy load to the auxiliary. Now I'll run a startup transient simulation and ensure the auxiliary voltage starts up correctly. I'll click the probe tool and click the desired node. We can see that the auxiliary voltage starts up and is somewhat higher than the output voltage, as we'd expect from a lightly loaded, unregulated output. Finally, let's examine the loss breakdown of the converter by choosing Efficiency Breakdown from the Simulate menu. We can click on the transformer and see both the DC and AC losses from the primary side and secondary side of the transformer. We can now examine how the transformer losses, including AC effects, vary as we suit the input voltage and the output current. I hope you've enjoyed this video and have learned how to use Eta Designer's new Magnetics Designer to quickly and efficiently design and analyze custom magnetics for your power converters. Please check us out at etadesigner.com to download a trial version and to view more instructional videos like this one. Thanks.